Welcome to CCSD Earth Science. Today we're going to be talking about plate boundaries and plate tectonics. We've already talked about how the Earth is broken up into plates and they're moving around during a process called continental drift. But we're going to get into today is more about how that's happening and what happens at some of the different plate boundaries. So plate tectonics is this idea that the Earth's crust, or the lithosphere, the outer shell of the Earth, is broken into several pieces called tectonic plates. So that's what we are referring to when we say the tectonic plates. It's what the continents and the ocean are on, or are a part of. Now, one thing that Alfred Wegener could not explain is how all of these plates were moving around. He just didn't have any information to back up his theory other than some of the evidence he had with fossils and mountain ranges and things like that. But he couldn't explain how these huge continents would be moving. Well, they finally realized what's happening is within the Earth. So here's a model of the Earth, obviously not drawn to scale. We've got the inner core, outer core, mantle, and part of the mantle is this layer called the asthenosphere, okay? And then the crust is right here that the plates are on. Within the asthenosphere, we have convection currents, where we've talked about convection currents before in weather, where you have something that warms up, it heats up, and because it's warm, it's less dense, so it rises. Well, as it rises, it moves apart. So places where the crust is moving apart is at these spots where the convection cells are drifting or are rising. And you have other places where those convection cells are now starting to come together and sync, and that's where we have another type of plate boundary called a convergent boundary. But this idea right here is what is causing plates to move. This diagram is also in page 10 in your reference table. Obviously it has a little more detail than what we have here, but definitely take a look at that. But the driving force, what is causing the plates to move, are convection cells in the asthenosphere. Now, plate boundaries. Okay, what that is just where the two plates are meeting. Okay, they're right next to each other. It's the boundary between two plates. All right, and page 5 in your reference table has a diagram with all sorts of plate boundaries that we have on the Earth. One type is a divergent boundary, where the two plates are moving apart. They're dividing, diverging. Okay, this creates a geologic feature called a ridge. Okay, so what happens, an example is like the Mid-Atlantic Ridge. It's underneath the middle of the Atlantic Ocean. The two oceanic crusts, or oceanic plates, are dividing. They're moving apart, and that creates this gap where magma rises up. Okay, so as it comes up, it cools on the surface, and it creates these ridges. So ridges are a feature of diverging plate boundaries. And one thing that you can figure out is that the younger rock near a diverging boundary is younger than the rock that's farthest away from it, because this rock is just formed, and then it pushes apart and new rock forms. So these two ridges used to be right in the middle. They were together. Okay, we talked about this with paleomagnetism. It's the same idea. The further you get from the center, or from the center of a divergent boundary, the older the rock will be. Now down here, you can see those convection cells. That's what's pulling those plates apart. Those convection cells are coming up and moving away and taking the plates with it. Okay, so that's what we have with a diverging boundary. So this is just a side view of it. Right here is a convergent boundary. Okay, this is when two plates move together. So basically what happens is you end up with oceanic crust. It collides with continental crust. The two come together. Well, continental crust has a much lower density than oceanic crust. So if something is more dense, it sinks. So that oceanic crust gets pushed down underneath the continental crust. All right. So this is called subduction. It occurs when dense oceanic crust, which is usually made of basalt, a type of rock, sinks below less dense continental crust, which is usually made of granite. Okay, so you can see that oceanic crust getting pushed underneath the continental crust. Well, if you think about what happens, what the temperature is like as you get further inside the Earth, it heats up. So you end up with some magma that forms that comes up to the top, okay, and you end up with a volcano. All right, and you see that a lot when you have two plates that are colliding, when you have a convergent boundary. Another feature that it forms is a trench right here, and this is all, if you imagine, this is all under the water, and then this is the shoreline. Right off of that, you will see a chain of volcanic mountains, usually. Okay, so this is a converging boundary. They're coming together. Now, when you have two continental plates that collide, because this happens once in a while, that's where you're going to end up with mountains. And the example are the Himalayan mountains. They are still forming today from the collision of the Indian, Australian, and the Eurasian plates. So neither one is more dense than the other, so they pretty much just push up, okay? And that's why the Himalayan mountains are actually getting slightly taller. And they're still forming today. So that's also part of a convergent boundary, is sometimes you're going to end up with two continental plates that collide. The last type are transform boundaries, and this is not necessarily plates that are going up or down or apart or together. They're sitting next to each other, so kind of like this, and one slides next to it. And that's what this is showing. It's a top view. The diagrams that we drew for the convergent and divergent boundaries, we're looking at it from a side view. If you were to take that area and cut it in half, this is looking down, okay? Because really you're not going to see any change if you're looking at a side view. It would look like that, sort of. But this is what you'd see from above. And the most popular or most well-known transform fault is the San Andreas Fault in California, okay? And if you look in page 5 of your reference table, okay, you're going to see all of the plates that make up the Earth's crust. You're also going to see the direction those plates are moving. There's arrows that show what direction the plates are moving in relation to one another. So definitely check that out, because that's got a ton of information. You'll need that a lot in this unit to figure out where all the plate boundaries are and how they're moving in relation to one another. The last thing we have here are hot spots, okay? Hot spots are pools of magma beneath the surface. So you've got the surface here, and somewhere beneath it is this pool or area of magma. Sometimes that magma will find its way to the surface, and you end up with a volcano on top. That's pretty much where Hawaii came from. There's a hot spot beneath Hawaii, okay, and this is actually kind of showing that same idea. Right now, there's a hot spot beneath Hawaii, and it formed that mountain right there, that island. Well, in the past, this plate, this oceanic crust, was shifted down this way, and this hot spot was underneath this one, and it was underneath this island, and it was underneath this island, and that is how all of those chain of islands formed, was because at one time the oceanic crust was above that hot spot. It reached the surface and formed that island. So today, the island of Hawaii is the youngest island in the Hawaiian island chain, and it's because it's still forming today, and that's where the hot spot is. There are definitely places where hot spots are not at the surface. The Yellowstone hot spot out west is there, but it's not at the surface. We know it's there because it's what causes Old Faithful and all of the the geysers and hot springs and things like that are all heated up from the hot spot. Because of that tremendous heat that we have in the earth near the hot spots, a lot of places like Iceland will use the heat from the earth for geothermal energy. So it's a huge energy resource for some of these places that are near a hot spot. Okay, so these are also located on page 5 in your reference table. They look like a little star, and they're located all over the world.